I'm not anti-machine learning. I'm not against machine learning. So, but I don't like the fact that everyone is trying to use machine learning, irrespective of whether it is the right tool for that problem or not. So it's like using one hammer for all the problems and everyone using the same hammer for all the problems.
Yeah.
That's my objection. If the machine learning is the perfect tool for that problem, use it.
Welcome to CFD for Industry. I'm Cade Beck, and I'm your host. In today's episode, I'll be interviewing Dr. Chennakesava Kadapa. I hope you enjoy our conversation, and please like, subscribe, and hit the bell so you don't miss an episode. All right, thank you for joining today, Chenna.
Thank you very much for the invitation. It's an honor to be on this series of podcasts. Thank you for inviting.
Yeah, absolutely. Could you briefly introduce yourself, where you started, and what you're working on now?
So my full name is Chennakesava Kadapa. People always find it difficult to pronounce. So my friends call me Chenna. So that's easy. So my background is in mechanical engineering. So like I had undergrad in mechanical, masters like master of technology in mechanical with specialization in machine design, and then I completed PhD in mechanical engineering. So now, so I have very like different experience. Like I was working in General Electric Aviation in Bangalore for 2 years before I did my PhD. Now, since my PhD, I've been in academia. So for since that is 2013. So 2013 till now. So I've been in academia like as a postdoc, as a research officer, and as part of the supercomputing wheels team. Now I am an like full-time academic at Edinburgh Napier University.
Awesome. Awesome. Can you start us off with what was your first experience with simulation? When did you encounter it?
So yeah, it goes back to a quite long time. Well, when I was in undergrad, so I was like I really had like the privilege of staying with really amazing people. These like in our part, like when we go to college, we have to live with like we have to share accommodation with others. So I was lucky enough to stay with seniors. So through them I came to know about all the different software. So this senior, like especially those in final year, they were working on like they were some of them were doing their projects using ANSYS. So that's how I came to know about ANSYS even in my second year of my undergrad. So that was really helpful. That's what it started my interest in the simulations. So I was excited. So they were doing lots of analysis. So I thought, okay, I should learn this. And then in the summer of after the second year, I went on. I learned ANSYS software for a couple of months, and then I ever since I was using this software. And then for my undergrad project, so I did use ANSYS for my project. I was doing some stress analysis, dynamic analysis, and so on. So that's how that's when I started. Yeah, I started something. And then in the final year, we had a really good lecture. So I have been privileged to with fantastic lecturers. So and yeah. So especially like in finite element method, we had a faculty member who inspired me a lot. So I took that finite element method course. So and then I did my undergrad project in ANSYS. So that's where everything started.
Yeah. What was it that was so inspiring about that lecturer? Was it just the way they taught? Did they use practical problems? Can you expound on that?
Yeah. So one main thing is the how they connect with students.
Hmm.
That's more important. Like the technical aspect comes later. Like how well they teach, that comes later. But how you interact with the students, that's what attracted me. Like how well he was caring for the students. And on top of that, he was really like fantastic in technical aspects. His way of teaching, like delivering the topics. So everything worked like perfectly. So he inspired me a lot. I even like to pursue masters. So yeah.
Yeah, that's awesome. Um, can you describe, in your experience at GE, you have that you developed an innovative modeling practice and that was approved by the International Review Board. Can you talk about that experience? How did you develop that? And what was that approval process like?
Uh, right. I don't remember much about the process. So that the how it started was like, so, like in most of the time in industries, at least where I was working in GE, so all the fatigue life calculations were based on the linear elastic stress analysis. But however, so one of the team like in USA, they found out that it is not good enough. So they wanted like, because they initiated this process. So we wanted to understand as a team how the elastic plastic materials affect the performance, because like it was found out during the assembly process that this retainer plate on which I worked on. So this is the retainer plate connecting the rotor with the stator, like with the blades. So that retainer plate undergoes the plastic deformation. So at that point, we didn't have a pipeline to do elastoplastic analysis.
Okay.
So all the analysis was limited to like elastic analysis with thermal stresses. So we had to create a new pipeline, analysis pipeline, by incorporating the elastoplastic material properties like hardening rule and all, and then do mesh convergence studies to match the simulation results with the experiments. So after everything, like it had to go through the quality approval, like in the review board. So yeah, that's the background story. I can't share much, partly because I don't remember all the details,
Yeah.
and some of it is confidential. So
Sure. But it sounds like that was a very formative experience for you early on, right? And what other lessons can you take away from that, or how else has that experience maybe been a defining moment for you as you look back on it?
yeah, so what I learned in GA, like in terms of the stress analysis using different software like Unigraphics for CAD, be it Hypermesh for meshing, ANSYS for simulation. So I have been using them ever since. Like in my PhD, if I wanted to generate some measures, I know which tool to use directly. Without, I didn't have to spend the time which people normally spend learning the tools in
Mm-hmm.
PhD. So I had this background industrial experience. I knew the tools, so which helped me a lot in my research.
Yeah. Speaking of your PhD, what went into that decision? Why did you return to get a PhD?
I always wanted to be in academia. So I wanted to do research. I wanted to teach. So like not just research, I do like teaching.
Yeah.
So I always wanted to do a PhD, but because of from some family financial reasons, I had to take up the industrial employment. So after my masters, I joined GE. I worked for 2 years, and then I came back to like academia to pursue my PhD.
Yeah.
And then yeah, so it was a really interesting story if I think about it. So I had options to go to Australia after my masters immediately, but I had to work. And then I was looking for PhDs. My interest was in dynamics. My master thesis was in nonlinear dynamics, so I wanted to continue the same, but I was looking for different opportunities. And then I was I wanted to do my PhD actually in fluid such interaction. That was my research proposal, and I found my like the PhD supervisor, Professor Wolf Detmer at Swansea. So he kindly agreed to supervise me, and I was fortunate enough to have the Zienkiewicz Scholarship for my PhD. So that's how it started. And then once I started my PhD, so I was offered to work on isogeometric analysis, which was completely off topic from fluid such interaction. But I am really lucky to have worked on that because that helped me a lot.
What
It's
was the
like
topic again? Can you say that again?
isogeometric analysis.
Okay.
So it is using CAD models directly for simulations, like NURBS based on instead of using standard Lagrange polynomials that we do in finite element method. So that topic isogeometric analysis was at the time recently introduced. It was a hot topic. So I worked on that topic to develop new mathematical formulations and new code for like incompressible hyperelastic materials or incompressible Navier.
Okay. That sounds fascinating. Very cool. For those who maybe don't know or haven't heard FSI and aren't familiar with it, can you give a brief beginner's introduction of what fluid structure interaction is?
That's That's a one at least 1 hour presentation. Yeah. So basically, so as the name implies, so fluid such interaction is the interaction of a fluid against a solid. So like for example, if we take a like some beam, okay, so we have a flexible beam or flapper, so which can, like, let's say it can deform, and then the fluid comes and then it hits it, okay, the solid deforms and then it allows the fluid to flow, and if it can sprint back, it pushes the fluid. So and then this interaction continues until there is either, like, if it is a steady equilibrium, it reaches an equilibrium. If it is unsteady flow, then it keeps oscillating. So that's one example. So it basically how the fluid and solid, the different domains interact with each other. So that's basically what we study in fluid structure interaction.
Yeah. So, one of the questions that was submitted for this was, what are some good resources for people to get started learning fluid structure interaction?
Yeah. So for fluid structure interaction, it does help if you have taken a course in your, like, undergrad or masters. But I understand that not everybody might have the opportunity to do this, because FSI courses are not usually covered in every engineering course, unless like you are in offshore engineering or like those kind of fields. FSI is not usually covered. So for people who are interested but didn't have that background, is first to be thorough with CFD. Because fluid such interaction, it is like an add-on on CFD. So you have to know how to solve, say, like fluid flow problems on fixed bodies. And then for the courses, so I have recently prepared a GitHub repository. So for the list of resources, like with the basic resources that like newcomers and also those with a little bit of experience can follow to improve their knowledge. So I can share a link, they can follow it and go through the list. So that it's difficult to talk about the good resource without having, like, without knowing their background, because there are some pre-required knowledge that people need to know to start working on fluid structure interaction. And also it depends, it's a vast field, like it depends upon the type of problem they want to solve. If you are working in oil and gas, like if you want to solve fluid structure interaction related to oil and gas or offshore, then it the suggestions would be different compared to, oh, like when someone wants to solve fluid structure interaction problems for biomedical engineering, for example, cardiovascular flows. So the fundamental is the same, but the methodologies we use are completely different. So that's why it's difficult to suggest resources for people to get started, because the requirements are sorry, vastly different.
Yeah. Yeah. I was recently talking with someone about this and I thought of an analogy. It's like riding a bike. I'm into mountain biking. And so there's some fundamental things that are very similar. But the difference between a mountain bike and a cyclist, like a road bike, are very different. They're designed to cover different terrains, right? The fundamentals are the same. But I feel like there's a lot of analogy that's
Yeah,
parallel to that in simulation.
exactly. Yeah. So depending upon the application, the type of tools we use, the types of resources we use would be completely different.
Yeah.
However, like, you have to have gone through at least learning CFD, and depending upon the application, like either some basics of dynamics or some FEM. So that is these three are essential if you want to get started on fluid structure interaction.
Yeah. That's great. Well, I'll include the link to your GitHub repository in the show notes for sure. So, what are simulation challenges that you see with FSI in industry?
The biggest challenge is the time. We have the tools available. Like ANSYS is capable, uh, Nastan is capable. We have Adina, Abatas has introduced FSI. Almost all the major commercial software do provide FSI simulation capability. Uh, One main challenge is the time, the amount of time it takes to run the simulation. Uh, like this, because we, like, whatever we are doing in FSI is on top of CFD. Imagine the amount of time it takes for you to run a, like, CFD simulation. and then multiply it by a factor of at least 2. So that's because like when the solid moves, you have to move the fluid mesh. You have to morph the fluid mesh. So this is an added cost. So, and depending upon the complexity of the FSI problem and depending upon how much the solid moves, we have to use different methods. Like the standard body fitted methods that we use in CFD are limited. So if your solid is moving in like a significant amount, we may need to use like adaptive refinement, or some may prefer overset meshes. So with overset meshes, adaptive refinement, there is an additional cost, and how well they scale on multiple, like if you go to supercomputing.
Yeah.
So the scalability and all these challenges, they do add up a significant like overhead on top of CFD. So that is the fundamental challenge. That is why we do not often see like full-fledged high fidelity FSI simulations in industry. And the second challenge, which is like even more critical, is the skill set needed to prepare a model for fluid such interaction. So because like you have two different physics, like if you call it like that, are two different sub problems. Fluid domain, you prepare, you do everything. CFD you solve. Let's take flow past the cylinder. You do CFD, you prepare the mesh, everything, and then you want to do FSI. So how do you couple it? You need to know. You need to know how the model behaves. At least have some basic insights into like what you expect. So depending upon that, you have to select additional set of parameters, like for the mesh morphing, mesh motion. So all of this. So this is even for a solid body, rigid solid. And if you go to flexible solid, then you need to know FEM. You need to know how to set up the model using like, let's say Nancy's, like Nancy's mechanical. Okay, you need to know how to set up this solid FEM model, and then how to couple them together. What could go wrong there, like how to set up the data transfer, where to set up the data transfer. And if you make a single mistake in data transfer, your results will be incorrect. That is the best thing you can get, or the simulation may not even work at all, like if you made some mistake. So there are so many things that can go wrong. Reaching a stage where you can properly set up the model and making sure that the results are accurate, because and there again there are so many things that can go wrong. Even if they don't go wrong, even if you get the simulation successfully running, the accuracy will be deteriorated. Even if you have a perfectly good solver for CFD and perfectly good solver for like solid mechanics, when you couple them, most of the time people use like what the methodologies to transfer the fields, like for example displacement and force, which are only first order. So like how to get this higher order accuracy, you don't have the control. So that's why like even if your CFD is second order, when the force transfer or data transfer is first order, so you are losing the accuracy. So you have to again spend that much amount of time and resources to get accurate results. So knowing all of this, like knowing what matters, knowing how to ensure the convergence and accuracy is very important. And this is the skill that's difficult to acquire because of the background knowledge that you need.
Yeah, that seems, as you're describing that, just very complex, right? CFD in and of itself is not an easy task to fully understand and get a good grasp on quickly. And then to add a separate domain and then the complications that come from coupling them, right? They're each difficult in their own right and require thoroughness. And so then coupling them and then being aware of what can go wrong contributes to the time, right? The skills and that and the time that it does take. And then just the compute time, right? Let alone the engineer's time. So that's difficult. What are trends that you see though in the industry? Do you feel like we're training engineers better to meet those challenges? Do you feel like we're going to see more of it? What do you feel like is the main bottleneck?
Main bottleneck is getting this training process. To be honest, I'm not quite familiar with what exactly happens in the industry. Like being in autonomy, I have limited knowledge at this point because I used
Yeah.
to know, but
Yeah.
after staying in autonomy for so long, to be honest, I don't know everything. But I think nowadays what I see is companies expect employees to know, which is the main problem, I would say. Like companies should be training their employees in terms of the tools they need to use
Mm.
to perform well in their job, like to solve the problems for the companies. I'm sure there are many courses available, like using ANSYS, different software, and doing FSI. But again, the companies need to be like coming forward to train their employees in these tools. This is not something you can learn in academia. I mean, in academia, you do learn some basic fundamentals. Like in universities, we don't be having projects where students need to run the simulation for days, like unless you are doing a PhD.
Yeah.
So, and if you get a PhD student who already worked on FSI, yeah, it's good. But if you don't have them to train them to be able to solve this multi-physics complex problem, that's where the challenge is. And depend considering the cost you need to incur. So I I think, yeah, it depends on the industry as well. I mean, they may not be able to afford it. So yeah, that's one of the challenge. The skill set, people skill set, training them is a big challenge.
Yeah.
And if you want to go forward, you have to spend like resources. You have to invest.
Yeah. Yeah, definitely a big topic there of workforce development and the return on the investment for the company. Because from the company's standpoint, they're in oftentimes a tough spot of trying to just deliver and get products
Exactly.
out,
Yeah.
and it's yeah, there's no easy answers.
There's no easy
So
answer.
yeah,
So if you think the problem is worth enough solving, then companies may take a judgment call about whether or not go on like training or may, so sometimes they may just outsource it as a project, like to some consultancy or some other.
yeah. What are the simulation challenges with FSI in academia? Similar, I'm assuming, skill set, getting someone up to speed to work on the problem in the short time of a master's or PhD project.
Exactly, yeah. It is the skill challenge in terms of the skill set is the same. At least in like in academia, like if you did a PhD student, you can train them. So you can take like at least the first year, help them like learn different tools. I think it's a little bit easier considering that you have like at least 3 years to complete a project. But
Yeah.
still, like you should get a good student who is willing to put effort, who is self motivated, because training itself is a huge part of it. Like they may know some, like they might have done some courses like CFD, and they might have done some courses on FEM, but not everyone have takes all the courses that are required. So
Mhm.
most of the time you end up learning one or the other. So if you come from CFD background, you learn FEM, vice versa.
Yeah.
But in terms of the challenges in simulating in academia, and there are apart from the skill set and training the students, there are no other challenge because we have the time at least compared to industry, and
Yeah.
we have the resource.
Yeah. That's yeah, that's good insight. Can you talk about, you said you always wanted to get a PhD and you really enjoy teaching. What is it that you feel like has been your goal with teaching? Like, is there a certain thing that you try to really approach as a teacher or as a lecturer professor in what you do? I know you mentioned one of the mentors that was really impactful for you as they approached the students, but can you talk about that and how that shaped your desire to teach and improve and develop the next generation?
Sure. So yeah, I would like to share my knowledge. So that's one of the motivation for me to teach. And I want to train like people who are like willing to put effort, who are, want to learn. Um, and through teaching, I also get to learn a lot. So if I'm teaching a new subject, which I did throughout my career, like teaching new subjects, you get to learn a lot. So that's how I I had the opportunity to learn machine learning, artificial intelligence. So my primary motivation is to share my knowledge. So that is why I like teaching. and I like to interact with people. Like we have all different experiences. I help them learn. So I like the process.
Yeah. Yeah. Do you feel like I noticed that in my program going through school, that the professors who had spent some time in industry, regardless of how long it was, had a very different approach to the way they taught. Have you observed that as well, and how your time in industry has shaped the way that you share your knowledge and the way that you deliver it?
Yes, yes, yeah, you are absolutely right. So the way we teach varies, and how you teach varies depending upon whether you have had some prior industrial experience or not. So with some industrial experience, you get to know like what actually happens in the industry, what are the things that matter, and then you have this experience and you can help the students connect. So in engineering, that's what really matters. So when they go out, they work in some industry, working on practical problems. So that really helps, and it also helped me a lot in my teaching in preparing the assessments. So
Mm,
like looking at the practice, okay, so this topic, like you can do this part, like whether some part of the turbine, part of the automobile. So it does help a lot, but we have to understand that not everyone can do it. So, but
yeah.
yeah, if you could do it, if you had that experience, it can be a positive thing.
Yeah. Yeah, I definitely observed everyone has their strengths, but I definitely resonated with those that had spent some time in industry and just their ability to tie it to some concrete uh, points, how the abstract.
Definitely, it does give you an edge,
Yeah.
because you have seen things in practice. Yeah, sometimes when you are teaching abstract concepts, if you don't have that experience, it can be really difficult to help the students see the connections.
Mhm. Yeah. So, not everybody can sign up and go take a class for you at Napier University, but you do offer a course through Flowthermolab, correct? And so that's something that they could take to get into FSI, right? You do an FSI introduction course through Flowthermolab. Okay.
So yeah,
We can
and
put the
yeah,
link
so
to that in the notes as well.
sure. So yeah, I have two courses. One is FSI, one is FEM. So
Okay.
again, my motivation there was to help the newcomers learn, like get introduction without having to go through the hassle. And I try to make the courses as simple as possible. But what one thing what I would like to I did was I do not allow the students to watch the videos just like that. So they have to watch it and maybe do one or two questions or quizzes like that. So at least they're following everything, because if they skip one or two topics, they have to again come back, and this is not good. So they must complete the let's say lesson 2.1 before going to lesson 2.2.
Yeah.
But
The sequence is instructive.
sequence, it matters a lot, especially in
Yeah.
these type of courses. And another thing, we made it really like, I don't say like really cheap, but not really expensive compared to the like other courses that are offered. I mean, so I want it to be accessible to like students who are like maybe working already in industry, not sorry, already working, or some employers already working, want to learn, get into a new field. So like that's why we made it really just have some, I would say, not that expensive.
Yeah. Yeah. Good value for what they're getting
Exactly,
with
yeah.
content where it's a win-win, right? Because you've got to have it make sense for you as well with all your responsibilities you've got going on. Transitioning to machine learning and the paper you wrote. So I think you'd shared this paper a while ago. I came across it and read it. And the title is Machine Learning for Computational Science and Engineering, a brief introduction and some critical questions. And can you discuss your motivation for that paper?
More than a motivation, it was a kind of annoyance and frustration with what was happening at that point, to be honest.
Yeah.
Because uh, even now things haven't changed much, but at least the hype has like calmed down a bit, but it is more widespread now.
Well, correct me if I'm wrong. You wrote that before ChatGPT was launched, right? Okay. Because I feel like the hype has actually gone back up again
Yeah, no,
in some ways. Maybe not.
some ways, yeah, but at least when it comes to machine learning for more like PDEs and all, it has come down a little bit, but it
Okay.
is more like it is wide like spread into different parts now. So
Okay.
yeah, my motivation was like to help people who don't have the background in simulations and who don't have the background in machine learning to see what the challenges are, to see what people are not talking, like what people are hiding. So I want to, in a way, like expose and make the practitioners and at least the newcomers who are entering the bandwagon to see what they are getting into. Yeah, that's why I have formulated these different questions. So which were not addressed in most of, not even now in any of the papers that that are coming out on like whatever the names they are coming up with, like pins or what, right? So that was my motivation, like to tell them, okay, so this maybe or may not be a good topic to work on, but these are the questions that should be addressed to have a bigger picture. It's not just like, oh, it is an amazing tool, yeah, like you can replace CFD and all. No, there are many other things that you need to know if you want to work in this field.
Yeah. And just to give an example of some of these questions, I've got the paper pulled up here. Um, one of them is, what are the computational resources used? What is the cost of generating the input data? What is the cost of training the neural network? What are the number of layers, the number of neurons in each layer, and the excitation of each layer, and how to choose them? How to avoid overfitting and underfitting? What are the tolerances and learning rate used, and how do they affect the training? For example, number of epochs, how much data is necessary to obtain a reasonably accurate solution to a problem? And then there's a few more that you go on. How accurate is the output of the trained network beyond the range of material parameters considered? How does the trained network generalize to other problems, changes in geometry, topology, discretization, initial conditions, etc.? What are the margins of error and the respective tolerance for input parameters? For example, how much can the input parameters vary for a given error margin? So when I read this, it did exactly that for me. It helped me understand the bigger picture, because one of the other things that I think we see often and in lots of places, but for example on LinkedIn, is a graphic of machine learning output, and it gives the time that it took to get that graphic, and then maybe the simulation time, and it's hours to seconds, right? Sometimes it changes a few orders of magnitude depending on who's posting it. But one of your key thesis points of this paper is that simulation was part of the life cycle time to generate that data, right? And that's kind of the crux of what I took away, that's not an apples to apples comparison at all.
Exactly, yeah, exactly. So whatever, like even if it takes 1 millisecond for with the AI, so whatever the 10 hours for the simulation, so it is finally 10 hours plus 1 millisecond. So that's what people are not saying. And like I understand that this is a marketing strategy by the companies and startups, okay, but that's fine. But the unfortunate thing is this is being bought by people in academia. So this is for me. I
Yeah.
understand, like in industry, okay, they have whatever the priorities or objectives they have. Okay, they do it marketing. That's fine. But in being in academia, we have to be critical of the technologies. But this is completely opposite to like how the boom is like even like spreading. So yeah, it's like looking at the recipes. Okay, 5 minute recipe. You get all the ingredients, and then you say, oh, you can cook in 5 minutes, but the amount of time you take to prepare that, you don't get the ingredients, like you don't get the data like from HelloFresh or Amazon, right? You have to generate the data on your own. And then the training, where do you train, like GPUs? So do we have enough GPUs? Do we have, even if you have GPUs, let's say I want to use some cloud source, cloud computing, I want to use Amazon, whatever, do we have the people
Yeah.
to use those resources? Do you have the employees like to train those? Because training you have to first get the data and then curate the data, input the data to the neural network, train it. Do we have people who can do this? and what is the trust of like those employees. So all the things, all the things they are like just swept under the blanket. So they don't talk about any of that. That's why I wanted to like inform the community. Okay, these are the things you have to at least try to answer these
Yeah.
questions now to better understand what you should be doing, what it all entails.
Yeah. And you give, for anyone who hasn't read the paper, I'll attach the paper in the show notes. Um, go read it. But one of the things that I particularly liked also was your breakdown. You give an example problem and what that would look like, and you provide some code for people to learn themselves and become familiar with the process, what the fundamental mechanism behind machine learning is, and um, one of the things that also stands out to me though is even in industry, like you talk about in industry, it might be a marketing strategy. But I was just talking about this with someone the other day, and they had worked for, we'll keep names blind, but they had worked for a company and another company, and they knew that their solver wasn't as fast as the competitor solver. And one of the things that they said, though, they said, we didn't try to sweep it under the rug because there were other things in our portfolio that when you took the whole life cycle made it faster. So they had some pre-processing that made things faster and other things on that. And so it just reminded me that that's a terrible marketing strategy even for industry, because industry cares about those things and you might wow them for a second, but it feels like in some ways that it's even just setting things back. And this is one of the things you talk about in your paper too, that anytime we're not transparent in any of this, it really hurts the community and it damages the community. And we already have enough maybe skeptics still on colorful fluid dynamics and other things that we don't need to add more to the scientific community. And we need less, and we need to be doing more to prevent that.
Yeah, exactly. Yeah, absolutely. And the reason I still like keep stressing this is, okay, in industry, okay, if something doesn't work out, it will die down, and people like the companies, people face the consequences.
Yeah.
You incur losses, but in academia, it's not like that.
Mm.
So you publish paper, you get a post, you get promotion, you publish rubbish, whatever you did, and that's it. There is no consequence.
Mm.
So there is no downside to doing bad research in academia. That is why it is even more important to discuss these topics openly and be more transparent.
Yeah. That's a great point. What started out as a provision to protect researchers, right, and their new ideas and the scrupulous opposition some of the early scientists faced, right? Like you go back far enough, people got killed for suggesting some big scientific breakthroughs. And so that has now transitioned to, in your mind, that we have removed any consequence for bad work.
Yeah,
That's, I've never thought of
unless
it
it
that way.
unless it turns out that people have manipulated data.
Sure. Yeah, we've seen the
Yeah,
Stanford example
unless it is
recently. And
extreme cases. So there are
yeah,
no consequences to doing bad research.
yeah. Definitely makes it difficult and improves or elevates the importance, like you said, of talking about things like this. So, maybe a few more specific questions to dive into the paper. What, again, for beginners, someone who maybe they've seen the hype, but they really don't know what machine learning is. What is machine learning at its fundamental core, and how does it work? Could you give an abbreviated example?
Right. Okay. So before I answer this, disclaimer: I'm not an expert in machine learning. Okay, but I know sufficient enough to apply this to simulation problems, which is good enough. Okay, so machine learning fundamentally is like surface fitting in hyperdimensional space. So if you are familiar with regression, linear regression, curve fitting, so this is exactly what we do. So if you look at the paper, so that's what I have shown. Like fundamentally what we are doing. We have the networks, we have the parameters controlling the network, and we use least squares to find the values of those parameters for the input we have. So like if you have done some experiments, if you found a relation using the experimental data, you must have used curve fitting regression. So this is exactly what happens in machine learning, but in a much at a much higher scale. Like where if you hear about ChatGPT, like there are billion parameters. So on a scale level, it is gigantic, but the concept is the same.
Yeah.
So that so if you understand this, if you understand like the regression least square fitting, and what you understand what is the input, what is the output, then you see the simulation side, you understand what is the input, what is the output, then connect them whether they are the same or not. So just like a one by one comparison. So whether can I replace this with this? So that helps you see how what is possible, what is not possible.
So one of the things that you address in your paper, and I want to be clear on this too, that you're not negative towards how machine learning can help us. It's not that at all. And I want to be clear to that because I think that in some of the concerns you're raising, people can mistake this for a negative anti-technology, anti-improvement, and that's not what I got out of it at all. So I do want to ask you, where do you see machine learning providing the most value?
Yeah, I very much like to thank you for that. So yeah, I'm not anti machine learning. I'm not against machine learning. So, but I don't like the fact that everyone is trying to use machine learning, irrespective of the fact that whether it is the right tool for that problem or not. So it's like using one hammer for all the problems, and everyone using the same hammer for all the problems.
Yeah.
That's my objection. That's my concern. Yeah. So if the machine learning is the perfect tool for that problem, use it. For example, inverse problems where we don't. For example, let's say you have a really complex material, okay, and let's say it is impossible to find an empirical relation like stress strain relation, constitutive relation for that complex material. Then machine learning could be the right tool for that, because since it is impossible to know the relation, so we use the neural network model to get the relation which we don't know, but maybe that's fine for some application. Maybe that's perfectly fine. So in those type of problems where we cannot have empirical relations, empirical functions, then machine learning is a right tool. But if you already know the function, it doesn't make sense again to replace this function with the neural network, because first of all it is less accurate, and it will be difficult to like either integrate or differentiate to use in our simulations, because you have to again use auto differentiation, which is expensive. So why do this if we can already do the if we're already doing it with a simple function?
One of the other things that I think you pointed this out too, that for those that have a big enough data set internally, like I work in consulting, for example, so machine learning has very low value at this point in my space for consulting problems because oftentimes it's a new problem every time. It's not like we're manufacturing product and we have all of this data in house. And so I think by industry or by not just by scientific topic, but by industry, there's also things that lend themselves to using it better as well. But I love that example of complex material. And it is the best fit for the job, right? We're looking at suitability. What is the most suitable approach to tackle this problem? We have an array of tools in our toolbox. And I think this comes back to what we were talking about earlier, just the skills that a good engineer with a good handle on decent tools can solve many problems. And we just need to flesh out our tool belt and quit obsessing on one tool given the problem. Anyway, so very, very good insights, Chenna. Thank you. Thank you so much. Um, any other comments on this paper? Any other final thoughts you want to leave people with about the paper, about machine learning in general?
Just one point, like if you're entering the field, if you want to know what machine learning for simulations is, read this, because there are some important questions that you should know, like you will ask yourself when you eventually start working on the project.
Yeah. And I can support that. As I read through this, it was obvious to me, maybe not explicitly, but implicitly, that you had spent time in industry. I don't think I knew this at the time that I read the paper, but just the practical questions that you ask. Because you even bring up that this, I can't remember how you phrased it, but investors, right? Like investors, people who are going to be investing in these tools and technologies are going to ask these questions at some point. Like you said, if they have a loss of profits, so it's great paper. Go read it. We'll link it in the show notes. Um, Switching gears here. So this question was submitted by our friend Julio, and he asked, I'm going to read the question and then we'll come back and break it down. So his question is, from your perspective and view as a scientist in CFD FEA, how do you see the future ecosystem of computational tools and infrastructure? Also, how do you see models such as discontinuous Galerkin and continuous Galerkin in the professional CFD field? Though they achieve higher order, why do you think they haven't been able to land solidly in the commercial realm of CFD while unstructured finite volume has? So let's pause it there, maybe tackle those two, and then we'll take the rest of the question.
Right. Yeah. So yeah, that's definitely an interesting question. I think that's something bothering almost everyone who are working in higher order methods. Yeah. So first, the main challenge is because to overcome the established giants in the simulation industry. So if you take like Fluent, Star CCM, and many others who have been in the field for almost like half a century, like almost 40, 50 years. So we're talking. So they have all their code base based on finite volume method. So going back and replacing the entire code base on the customer base who have been using Fluent and tell people that hey look overnight we are going to replace all our finite volume codes with DZ, it's not going to work. So these new tools they have to be they have to come out from new players in the field. So that's how I see it spanning out. For example, if we take Crumzol CFD is based on finite element method. So if you have new players come in and those players they do adopt the new technologies, whether it is FEM or like DG or CG, or maybe there is some other new technique that comes up. Let's say, for example, or like for example SPH. So SPH. So the main challenge is overcoming the established base and overcoming the competition. So that is the main challenge. So I don't know how this is going to span out because this is a very complicated field with so much like billions and billions of dollars, right? Like we are talking about in terms of the revenue investment for for by these players themselves and also their customers who use the software. So it's a difficult problem. I don't think I have all the knowledge to say one way or other. But it is interesting to see what is coming up. So in terms of like Crumzol, like maybe there is something similar that comes up that embraces DZ that can show the real potential of DZ. Yeah, maybe we'll see. So recently, like there is a core form. It's not completely fluid mechanics, but they highly focus on solid mechanics. But they don't use conventional finite element method. They use what is called as isogeometric analysis. So like we had briefly touched on my PhD topic.
Yeah.
So they seem to be doing really well. So some that's what I'm saying. The new players must be there, like must be the ones bringing these technologies for.
Yeah. There's an interesting book. It's called The Innovator's Dilemma. It's by Clayton Christensen. He's a business professor at Harvard. And that's exactly one of the things he talks about a disruptive technology that a legacy company, their entire structure, both financial and organizational, is not suitable. So the lens at which they look through new developments, the basis for making all of their investment decisions, it's not worth it to them. And so he talks about if they are going to do it, they have to spin off a separate entity to tackle that thing, and they have to be measured differently in the terms on their investments and returns. And that's something that I see again and again. And then what you see happening even now in this space, there's a lot of acquisitions that have happened in the last even 3 to 4 years in this space of, I think one of the most recent ones that comes to mind is Siemens acquiring an SPH code and releasing that with their most recent release. Um, but I just think that's very striking about some of the realities of innovation and business. And that's not what we're trained in, right? Like when we look at this stuff, but it does play a role. And so the more we understand about some of those things, the better engineering decisions we can make. And the easier it is for us to maybe understand why some things are happening and why some things aren't happening. So that's great insight. I realized that I probably cut the question in a weird spot. Julio has a follow up to it. And he says high order finite volume seems to be the heavy backpack in finite volume practitioners, but discontinuous Galerkin doesn't show a solid roadmap. Why do you think this is the reason?
Yeah. So higher order finite volume method, it is the obvious road, obvious next step. Because you have the finite volume base, like for example, you take Fluent, like star system. They have the finite
Mm-hmm.
volume code. They don't have to change much. It is just the one algorithm they have to implement internally. So it is the obvious, like straightforward step.
Yeah.
But achieving higher order accuracies using finite volume method, there are a lot of challenges there because of the way the finite value method fundamentally works. Like we have to spread your stencil over as opposed to increasing the like nodes in a finite element method. In a finite element method, you draw inside to increase the accuracy. Like you add more nodes inside the element. If you take a triangle, you keep adding on more and more nodes inside. But when you want to increase the accuracy in finite volume, you spread away over like over the neighbors to increase your neighborhood. So it so because of that, like getting accuracy can be really challenging. And like as you increase the stencil, you are increasing the bandwidth. There are so many things, and also uh, like how we don't know how these streams like flux streams work with the higher order, how stable they are. So these are the challenges. I think people are have done a fantastic job like in improving the stability accuracy of the streams for finite volume method. We will see them coming up definitely, because that is the obvious choice, like obvious road ahead
Yeah.
in all the major partners. But again, coming back to DG, there are still some challenges. DG is not good if you stick to lower order, because when compared with like with the CG, like continuous Delarkin, discontinuous Delarkin, the problem size increases by a factor of 8 in 3D if you if you are within the first or second order. So that is not really promising. So if you want to use DG, you have to go to higher orders, like around like 8, 10, something like that, which is where you get the computational benefit. But the challenge is mesh generation. So if you want to adopt it in industry, we need to have the mesh generators, which is the big bottleneck to again, like if any new startup want to embrace DZ and take it forward, they have to come up with a mesh generator to use DG, especially in higher order. In academic world, yeah, we do have, and most of the time we do like some patchwork. We get the CG mesh and write some code to transform the CG mesh into DG mesh, and there are many variations about how people do this, but there is no like really robust tool like mesh generation tool to take DG forward. That's where the challenge is, and
Yeah.
there are some challenges in terms of the solvers as well. But once you have the mesh generator for the complex real world problems, the other challenges can be overcome, because like once you get the push, once the industry is interested, there is that's a motivation to work on the solvers.
Yeah. So this is new to me, and I'm not familiar with much of the discussion, but I understand fundamentally finite volume, right? You're expanding the amount of communication that happens with a higher order method because you're including more information from more cells surrounding the cell. In finite element, you're going inside for the coefficients as you increase in order. And so it's different that way. So how does discontinuous Galerkin fit? Is it, for beginners, how would you classify that method? And why is the meshing what makes it the bottleneck?
Right. Okay. DG is CG with tracks. So you take CG mesh, you cut it along the mesh lines. Then each element, so they are disjoint from the neighbors. So in DG, the elements are not connected. So the elements, they don't share the edges. Sorry, they don't share the nodes at the edges. So in CG, the two elements share the nodes at the edges. So this is the difference. In DG, they are disjoint. So that is why we can capture the pressure jumps using DG. This is the major motivation for using DG for CFD. So otherwise we can stick to CJ, and if you want to solve it in compressible like flows without like shock waves, CJ is perfectly fine.
So at the risk of stating the obvious, DG gives us greater control over the nonlinearity.
I wouldn't say nonlinearity, but jumps in
Okay,
the
the jumps. Yeah, because you can have nonlinearity without jumps. Yeah,
without
got
jumps.
it. Yeah, yep. Okay. No, that makes sense. Do you see much research or development in the Julio's question, back to the roadmap, right? It seems that DG doesn't have a clear roadmap. Are you seeing more research in that area of mesh generation for DG? Are we seeing more activity there?
Um, there is some activity definitely, but again the challenge is in like getting funded. So
Yeah.
uh, it's impossible, not impossible. It's very difficult to convince the funding councils to fund this type of projects. So because of that, the development is ideally limited to those like established big groups. Like I don't want to name the places, but you can imagine like those places with some history. So even there, it is challenging to still convince that whatever we want to go ahead with this.
Yeah. Okay. Interesting. One more follow-up question. I think this comes back to the first question. So again, the first question was, from your perspective and view as a scientist in CFD FEA, how do you see the future ecosystem of computational tools and infrastructure? And then the follow-up to that one is about computational infrastructure. What are your thoughts of the current state of pushing more GPUs for faster turnaround? Do you think industry and media have not been transparent?
GPUs. So GPUs, if you have a single physics without any data movement, GPUs may be the best. Again, like if you are doing some aerodynamics, like for aircraft, just like air flowing over some object, GPUs, yes, use them. That's fine. But if you have some other complex multi-physics problems for which you need data transfer, no, we can't use GPUs. We have to use CPUs, because once you move data in and out of GPUs, you are losing the throughput. You are losing the speed up that you get. So yeah, again, like there has been a lot of push towards GPUs, especially because of the AI. So people even like there is people are working to use AI infrastructure, both hardware and software infrastructure, and adopt it for CFD. So that means like artificially developing solvers just because there is hardware. So I don't know how beneficial it would be. I don't know. We have to wait and see. In my feeling, they're not good. I mean, you have to look at the physics. You have to look at the solver, like solver in the sense the methodology you use, and see if it is beneficial to parallelize it on CPUs, like using MPI and all, or
Yeah. One of the things that stands out to me about this, and I have to give credit to Joshua Strotbeck for this, but one of the things he often talks about is when you compare these things, it's often better to do a price-based comparison of okay, what's the cost of the GPUs versus the cost of the equivalent, or what's the performance of the GPU? How much did it cost? And then how many CPUs could you get for that same cost? And that's one way of looking at it that maybe is a little more comparable, at least for the industry side of things, right? Of what the return's going to be.
Exactly, yeah. And that's what yeah, my next point is. So imagine that you are a customer. So
Mhm.
people always think from the development side, but they don't think from the customer side. Majority of, okay. Think of think yourself as a customer. Okay, I want to buy a workstation with, let's say, 30 crores or 50 crores. Okay, I want to buy a workstation and to run simulations. So if I buy a workstation with, let's say, 30 crores, what is the cost? But if I have to use your solver, if I want to use your solver, and if I need a GPU that costs me like 20K, 30K, whereas I can buy a workstation with 30, 50 crores, like for half of the price, then why would I want to use your solver, like buying the GPU at a much higher cost?
Yeah.
So that's the thing the company should be asking. We often, at least like in LinkedIn, it is really from the advertisement point of view. So sales, sales, sales. So lot of hype over there, lot of overselling. So people have to take a step back. At least those who are like in the industry and working in the field. So they have to ask these questions. That's
Yeah.
when things make sense. Yeah, GPUs are good, fantastic. Okay, they give you 100 times speed up. Yeah, but people may not be able to afford GPUs. Not all of them.
So coming back to the ecosystem of computational tools and infrastructure, do you think, or are your feelings that we're going to see more cloud-based stuff anyway, and we'll see less workstations in offices? Or do you think that depends on industries and how protective they are of their data, right? I think I was just at a conference recently, and it was about data security. One of the keynote presentations was about data security and the concerns that big companies and big organizations are having with data security. And their anyway, it's just another layer to this that I hadn't really been on the forefront of my mind as day to day doing CFD, right? But what are your thoughts on the ecosystem of how we're going to see cloud navigation, or people migrating to the cloud or staying on premise?
Yeah, all the big companies like Boeing, Airbus, like even when it comes to automobile, BMW, all the big companies, I don't see them going to cloud, because basically because of data security, and also because they already have the established framework at their disposal. Okay, so those who are going to use the cloud are small to medium sized companies who may not have the required hardware, who may not have the skill set. So they simply want to use some tool available online, whatever it is, and hardware available at the, like in the browser, that you can access through a browser on some cloud, to simply do some design iterations.
Yeah.
So which is okay, but again, like this is, so we should have all the options. It's not, again, like the unfortunate trend nowadays is like everyone wants to go in one direction. So that's not how it should be. You have to have different options,
Yeah.
and people should use, depending upon whatever they find it best, depending upon the limitations and the resources they have.
Yeah. And coming back to, um, you mentioned this earlier, that there's so much information out there that we are just awash in information. Like and it's, well, most of it's good. Let's be positive and say most of it's good information and accurate, right? Um, but that just be in and of itself becomes a problem of how do you decide where to spend your time and what you're gonna pick to go all in on and figure out. Because one of the things that I see is, oh, so and so's doing this, so we'll do this as well. But there's a key difference of why so and so is doing that and why that may not be good for you doing it. But because there's so much information, they're trying to speed things up. And so again, I keep feeling like implicitly it comes back to when you really understand the problem you're trying to solve and what goes into it with fundamental physics, then a lot of those decisions become clearer of why yes or no, or they become, it doesn't matter. Let's pick one and move forward. Would you agree with that?
Yes, yeah, definitely. Yeah, and I do see the problem with a lot of information. Yeah, so there is like if I open YouTube and search for some topic, you get like so many videos. Which is the right one? Not the right one.
Yeah.
Which one should I follow? That's the key question. So it comes with experience. It comes with experience, and people need to have patience. So nowadays, I see a lot of like impatience. Right? Okay, sir, I want to do this. How do I do this? Okay, first go online, do some search, and this is something I'm also seeing like literature review. This is almost missing. People don't do literature review. If it the idea behind literature review is to find out what is there, what is not there. You don't need to know everything, but you will know some things which will guide you, and then talk to your peers or your supervisor. Then they'll give you more information. But you can't be asking others for help without yourself spending some time and effort. You have to do this. Sometimes it is difficult, understandably. That is why you need patience. So,
Yeah.
and it's an unfortunate thing that we have so much information. Fortunately, there is
Yeah.
yeah. So if you have too much information, if you want to filter out, pick randomly some resources, just scan through them, see which one clicks, which one you can understand better. So there some may understand like one one channel, one YouTube channel, they delivery better. Some may not understand it because of the background. So just pick, don't spend too much time. Just quickly scan and see if you can follow it for a longer time. So this is how like we have to come up with some strategies
Yeah.
that suits you best. There is no single strategy that fits everyone. You have to build up that strategy developing.
Yeah. We could spend a whole day on how to properly ask for help on LinkedIn when you need help, right? I know we have both posted about that multiple times. So don't just send me your problem statement and saying, how do I do this?
Exactly, yeah.
Yeah.
So people like say, okay, I want to write UDF. ANSYS has manual. Go read the ANSYS manual. If you have an error, if you can't figure out, okay, ask in a forum. There are different places for different purposes.
Yeah.
So
Yep. Yeah. Good points. I think we've also had this come in throughout our discussion of the irony of our times is that just at the exact moment when we need critical, clear thinking is when it's so easy to get caught up in busyness and feeling like you're making progress because some of the metrics are maybe so hollow or easy to see, but touching on it with patience of good work takes time, and the point is to change you. Like if you think of a PhD in school, right? Certainly you're going to learn and you're going to become an expert in something. And at the undergraduate level, you're going to learn how to learn. You're going to develop a framework. The product is you. And that's what you should be investing in. And so just any thoughts on that in closing of for people really wanting to get good. And I think we're kind of ending where we're beginning, that the fundamentals. But do you have any more comments on uh, helping people get good at the fundamentals?
so there is no shortcut to getting good at fundamentals. So sometimes you have to remember, right? We call it rote learning. So you have to do that,
Mm-hmm.
but that requires dedication. So you have to dedicate some time to learn some concept. So for we can't talk about everyone else, but at least when it comes to our field, at least the one we are talking simulation and all.
Yeah.
So mathematics is the key. So you have to be really good at maths. You don't need to know everything in math. You need to know like matrices. you need to know basics of differentiation, calculus. And now, since we are talking about computers, you need to be good at programming. So learn. If you are not good at this, find good sources, talk to people, dedicate time to learn this. So do not think about tomorrow or 2 days or 2 weeks from now. Think about next 5 years. Think about next 5 years, because you will be there in 5 years, and you want to see like how things have changed. So that's why dedicate even couple of hours every week. Learn the subject that you want to learn, that you must learn to progress. So 2 hours per week is not much, but if you it accumulates.
Yeah. It compounds too.
Yeah, exactly.
Yeah. Yeah. Well, thank you so much. One final question for you. What do you know now? If you were going back to give Chenna advice at your sophomore year when you were living with those seniors, what would you tell yourself? If there were one thing that you could tell yourself about simulation, what would you tell yourself if you were giving yourself advice?
I don't know. It's a very difficult question. I mean, um, I would say like learn more programming.
Programming?
Learn more programming, because at that time we didn't have any like we had to see course like in first year, but
Hmm.
after that we didn't have any programming.
Okay.
We had a CAD, AutoCAD, we had ANSYS and other software, but no
Yeah.
program. So learn programming.
Programming.
That's one advice I would definitely give to Chenna back
Yeah.
in undergrad. Yeah.
Yeah. No, I always like asking that question because I think it's interesting with your experience and perspective when you look back on something that has really been pivotal for you or helpful. Um, just interesting. So thank you so much for your time, Chenna. Really appreciate it. If someone wants to either get in touch with you, maybe a research collaboration, um, or just collaborating on anything, can reach out to you, what would be the best way to do that? LinkedIn?
Either LinkedIn, I'm open either way. So whichever method they feel is convenient. So either LinkedIn, or they can directly email me to my like staff ID at Napier.
Sure.
So yeah,
Okay.
perfect. Yeah, I'm open to collaborations, even for like just a discussion. If you have questions, or if you want to just talk about simulations, any topic, FEM, CFD, I'm open. Or I'm also open to like help prepare courses or one like workshops, what plan and deliver workshops. So if at all anything you're interested in any of the aspects, drop me an email or contact me through LinkedIn.
Awesome. I'll be sure to put your website in the show notes as well so they can find all your contact information there. So perfect. Thank you so much, Jenna.
Thank you, Ted. Yeah.
Thank you for listening. Really, thank you. Did something about this episode stand out to you? If so, please go ahead and share it with others on LinkedIn or other social media so they can find this as well. See you next time.